Lying just beneath everyday reality is a breathtaking world where much of what we perceive about the universe is wrong. Physicist and best-selling author Brian Greene takes you on a journey that bends the rules of human experience.
Why don't we ever see events unfold in reverse order? According to the laws of physics, this can happen.
It's a world that comes to light as we probe the most extreme realms of the cosmos, from black holes to the Big Bang to the very heart of matter itself.
I'm gonna have what he's having.
Here, empty space teems with ferocious activity. The three-dimensional world, merely a mirage. The distinction between past, present, and future, just an illusion.
But how could this be? How could we be so wrong about something so familiar?
Does it bother us? Absolutely.
There's no principle built into the laws of nature that say that theoretical physicists have to be happy.
It's a game-changing perspective that opens up a new world of possibilities. Coming up, what if new universes were born all the time?
In this picture, the Big Bang is not a unique event.
And ours was one of numerous parallel realities.
Somewhere, there's a duplicate of you and me and everyone else.
Are we in a universe or a multiverse? The fabric of the cosmos, right now on Nova.
New York City. They say there's nowhere else like it. Home to 8 million people. Countless structures, monuments, and landmarks. Every one of them unique. Or so we think. Uniqueness is an idea so familiar we never even question it. Experience tells us people and objects are one of a kind. Why else would we visit museums and collect great masterpieces? Yet, a new picture of the cosmos is coming to light in which nothing is unique. Not that the world's great masterpieces are fakes. Instead, I'm talking about something far more profound. A new picture of the cosmos that challenges the very notion of uniqueness. One in which duplicates are inevitable. And that's just the beginning. There might be duplicates not just of objects, but of you and me and everyone else. But if this new picture is right, where are these duplicates and why haven't we ever seen them? The answer may lie outside our universe. There was a time when the word universe meant all there is, everything. The notion of more than one universe, more than one everything, seemed impossible. But perhaps, if we could go beyond our solar system, beyond the Milky Way, even beyond other distant galaxies, past the end of the observable universe, we'll find that there's more, a lot more, that our universe is not alone. There may be other universes. In fact, there might be new ones being born all the time. We may actually live in an expanding sea of multiplying universes, a multiverse. If we could visit these other universes, we'd find that some might have basic properties of nature so foreign that matter as we know it couldn't exist. Others might have galaxies, stars, even a planet that looks familiar, but with some surprising differences. And if there are an infinite number of universes in the multiverse, somewhere there's a place where almost everything is identical to ours, except for the slightest details. Like maybe there's another Brian Greene who ends up in a different line of work.
If the multiverse is indeed infinite, then one is going to have to confront a lot of possibilities that are very hard to imagine.
There'll be other places where there'll be Alan Guths who will look and think and act exactly like me, as well as many where there'll be Alan Guths who look and think almost exactly like me, but with some small differences.
Is it science? Is it a part of metaphysics? Is it just philosophy? Is it religion? Physicists tend not to ask those questions. They just say, let's follow the logic. And the logic seems to lead there.
However unfamiliar and strange the multiverse might seem, a growing number of scientists think it may be the final step in a long line of radical revisions to our picture of the cosmos. That is, there was a time when we thought that the Earth was at the center of the cosmos and that everything else revolved around us. Then along came scientists like Galileo and Copernicus, and they showed us that it's the sun, not the Earth, that's at the center of our solar system. And our solar system, it's just a little neighborhood in the outskirts of a gigantic galaxy. And our galaxy, it's one of hundreds of billions of galaxies that make up our universe. Now, all of these ideas sounded outrageous when they were first proposed, but today we don't even question them. The idea of a multiverse may be similar. It simply may require a drastic change in our cosmic perspective. On the other hand, some scientists think that the multiverse is nothing but a dead end for physics.
I'm very uncomfortable with the multiverse. To become solid science, it's got a lot of growing up to do.
You know, it exists in the same way that, angels might exist.
We have to make our bets. And I think right now the multiverse is a pretty good bet.
I think there's a good chance that the multiverse is real, and that 100 years from now, people might be convinced that it's real.
So where did this idea come from? And what's the evidence for it? Well, several surprising discoveries suggest that we really may be part of the multiverse. The first of these discoveries has to do with the generally accepted theory of the origin of our universe, the Big Bang. According to this theory, our universe began some 14 billion years ago in an intensely violent explosion. Over billions of years, the universe cooled and coalesced, allowing the formation of stars, planets, and galaxies. As a result of that explosion, the universe is still expanding today. But if you could run the history of our universe in reverse, all the way back to the beginning, you'd find that the Big Bang Theory tells us nothing about what sent everything hurtling outward in the first place.
It's called the Big Bang Theory, but the one thing that it really says nothing about at all is the bang itself. It says nothing about what banged, why it banged, or what happened before it banged.
So, what fueled that violent explosion? What force could have driven everything apart? The quest to figure that out would bring scientists face to face with the multiverse. One physicist whose work unexpectedly helped lay the foundation for the multiverse idea is Alan Guth. Today, he's a professor at MIT. But back in 1979, Guth and a colleague, Henry Tye, we're pursuing a new idea about how particles might have formed in the early universe.
Henry suggested to me that we should maybe look at whether or not this new process that we were thinking of would influence the expansion rate of the universe.
Guth and Tye hadn't set out to investigate the expansion rate of the universe in the first moments after the Big Bang. But Henry Tye's question caused Guth to review their calculations one more time.
I stayed up quite late that night and went over the calculations very carefully, trying to make sure everything was correct.
As the night wore on, Guth discovered something extraordinary in the equations describing how new particles might have formed in the early universe.
And came to the shocking conclusion that these newfangled particle theories will have a tremendous effect on the expansion rate of the universe. The kind of process Henry and I were talking about would drive the universe into a period of incredibly rapid exponential expansion.
What Guth found in the math was evidence that in the extreme environment of the very early universe, gravity can act in reverse. Instead of pulling things together, this repulsive gravity would repel everything around it, causing a huge expansion.
I immediately became very excited about it and scribbled out the calculation in my notebook, and then at the end I wrote "spectacular realization" with a double box around it. Because I realized that if it was right, it could be very important.
By discovering this repulsive gravity, Alan Guth had unintentionally shed light on the very beginning of the Big Bang. Described mathematically, this force was so powerful, it could take a bit of space as tiny as a molecule and blow it up to the size of the Milky Way galaxy in less than a billionth of a billionth of a billionth of a blink of an eye. After this incredibly short outward burst, space would continue to expand more slowly and cool, allowing stars and galaxies to form just as they do in the Big Bang Theory. Guth called this short burst inflation, and he believed it explained what set the universe expanding in the first place. The powerful, repulsive gravity of inflation was the bang in the Big Bang. But despite having made a momentous breakthrough, Alan Guth had an even more pressing concern.
I had no idea what my employment might be. I was really looking for a more permanent job.
The inflationary universe scenario looks very exciting.
So I went on actually a pretty long trip giving talks about this.
I call the inflationary.
Suddenly, this idea caught on.
Talks about inflation were packed with people from all areas of physics.
Lots of astrophysical theorists, including me, got very enthusiastic.
It was a very, very exciting time.
If you have a really good idea that allows other people to move the field forward, people are going to pay attention.
An amazing feeling that suddenly I had crossed that gap from being an unknown postdoc to being one of the major players. It was very hard to absorb, but it certainly felt good.
One reason inflation was so exciting was that it made predictions that could be tested through observation. Scientists realized that if the theory were correct, evidence for it should be found in the night sky. Imagine that we could shut off the sun and take away all the stars. If our eyes could detect the rest of the energy that's still there, we'd see a warm glow everywhere in the cosmos. This sea of radiation is called the cosmic microwave background. It's the last remnants of heat from the Big Bang itself. Theory predicted that the violent expansion of space during inflation would leave an imprint on this radiation. These telltale fingerprints would form a precise pattern of temperature variations, slightly hotter spots and slightly colder spots that would look something like this. But it would be about 10 years before the technology was sensitive enough to test this prediction. Then in 1989, NASA launched the Cosmic Background Explorer satellite, followed by a second satellite, WMAP, in 2001 that would put inflation to the test. The missions measured the radiation with tremendous precision, and the results were stunning. The temperature variations found in the cosmos were an almost identical match with the predictions of the theory of inflation.
It's just a theory, mathematics on the page, until it makes predictions that are confirmed. WMAP found what the math of inflation predicted. That is enormously convincing.
So inflation has had a number of chances now to fail. It made predictions, data came in, and inflation has come through with flying colors.
Guth's work on inflation, along with that of other physicists, was hailed as a milestone toward understanding the origin of the universe.
In the process, it expands.
But soon, two Russian physicists would discover that the equations of inflation held a shocking secret. Our universe may not be alone. One of these physicists was Andrei Linde, who had already made pivotal contributions to inflationary theory. The other was Alex Vilenkin, who happened to attend one of the talks Alan Guth gave during his road trip.
He gave a wonderful talk. I haven't met him before, but what I heard was rather unexpected. In one shot, inflation explained very well many features of the Big Bang, and was quite remarkable.
Why the universe is the way it is.
So I went home greatly impressed.
Alex Vilenkin was so impressed that for months afterward, he couldn't stop thinking about inflation.
Usually I have my thought of the day in the shower, which I tend to take long.
The more Vilenkin considered the process of inflation, the more he wondered about what would make it stop. How would a region of space transition out of inflation? What exactly would happen at the moment inflation ends?
As I thought about it, it turns out that the end of inflation doesn't happen everywhere at once.
Vilenkin suddenly realized that if inflation doesn't end everywhere at once, then there's always some part of space where it's still happening.
So in this picture, the Big Bang is not a unique event that happened. There were multiple bangs that happened before ours, and there will be countless other bangs that will happen in the future.
It was a striking and unexpected new picture in which inflation would stop in some regions but always continue somewhere else. New Big Bangs are always occurring, and new universes are always being born, yielding an eternally expanding multiverse.
Linde and Vilenkin in particular pushed the idea that inflation might never end, that this ballooning process could happen over and over again, giving one universe after another after another.
So, was this a revolution in science or a theory that's full of holes?
The idea became known as eternal inflation, and you can picture it something like this. Imagine that this block of cheese is all of space before the formation of stars and galaxies. Now, according to inflation, space is uniformly filled with a huge amount of energy, and that energy causes space to expand at an enormous speed. As it does, here and there the energy discharges, sort of like a spark of static electricity.
But this is like static electricity on a cosmic scale. And when it discharges, all that energy is rapidly transformed into matter in the form of tiny particles. That process is the birth of a new universe. what we have traditionally called the Big Bang. Inside these new universes, which are like holes in the cheese, space continues to expand, but much more slowly. And sometimes galaxies, stars, and planets form, much as we see in our universe today. Meanwhile, outside of these new universes, the rest of space is still full of undischarged energy and is still expanding at enormous speed. And more expanding space means more places where the energy can discharge into more Big Bangs and create more new universes. And that means this process could go on forever.
In other words, when it comes to eternal inflation, that cheese is more like Swiss cheese, in which new universes endlessly form, creating a multiverse.
The multiverse, a profound implication of eternal inflation. But as Alex Vilenkin would soon learn, one that would not be easily accepted.
I thought I realized something important about the universe, and I wanted to share this with my fellow physicists. And one of the first, of course, had to be Alan Guth.
Now, we know that quantum fluctuations in the scalar field are different in different regions in space.
I thought he would be excited about it.
As a result, in some regions,
But actually, this encounter didn't go as planned.
inflation will last longer than in others. The delay of inflation...
As I was describing to him my new picture of the universe, inflating regions and so forth,
expansion.
I noticed that Alan is beginning to doze off a little bit. Actually, I was, of course, very unhappy about that, so I thought that I probably should go.
One problem with the concept of a multiverse was that there seemed to be no way to detect it. Not only is each universe expanding, but so is the space in between them. And that means that nothing, not even light, can travel from any of the other universes to reach us.
Physicists did not really respond very well to this idea of eternal inflation. Once I said that I'm going to tell them something about things beyond our horizon that cannot in principle be observed, most of them just lost interest right there.
Alex Vilenkin thought he was onto something big, but others were skeptical. So Vilenkin reluctantly tried to put his work on eternal inflation out of his mind.
Who wants to talk about a universe you're never going to see? The multiverse can't make predictions. It can't be tested. You could make the case that it's not really science.
How can you ever be confident of it when you can't see the other parts of the multiverse? We can only see our little patch, our little expanding cloud of galaxies. How are we ever going to know?
You can't prove the multiverse exists. It's not wrong. You can't prove that it doesn't exist. So why should we believe it?
Alex Vilenkin tried to stop thinking about the multiverse. With no hard evidence to support it, the idea seemed to have hit a dead end.
Many people thought that it's just not science to talk about things that you cannot observe. So I did not return to the subject for almost 10 years.
Meanwhile, Vilenkin's Russian colleague Andrei Linde kept the flame alive. He had independently come up with his own version of eternal inflation, but unlike Vilenkin, he would not be deterred.
Maybe I am a little bit more arrogant. When I got the idea for this multiverse, I understood that this may be the most important thing which I ever do in my life. And then if somebody doesn't want to hear it, that's their problem.
Linde published more than a dozen papers on the subject, but his work would meet an equally chilly reception. It seemed no one wanted to hear about the idea of a multiverse. If the equations of eternal inflation were the only clues pointing to the multiverse, that's where the story might have ended. But the multiverse idea would gain some unexpected support from two completely unrelated areas of science. One was an idea called string theory, designed to explain how the universe works at the tiniest scales. The other was an astounding discovery made by astronomers exploring the universe on the largest scale. A discovery that's utterly mysterious if there's only one universe, but if we're part of a multiverse, it's a whole new ballgame.
It has to do with the expansion of the universe, and it's easy to explain using a baseball. Now, if I toss this ball up in the air, we all know what will happen. As it rises, it slows down because of gravity. Now, astronomers knew that the universe was expanding, and they assumed that the expansion would slow down because of the gravitational pull of stars and galaxies, just as the ball slows down because of the gravitational pull of the Earth. But when they actually did the measurements, they found something astonishing, something that rocked the foundations of physics. They found that the expansion is not slowing down, it's speeding up. It's as if I took this baseball, and when I throw it, instead of slowing down as it rushes away, it speeds up. Now, if you saw a ball do that, you'd assume there's some invisible force that's counteracting gravity, pushing on the ball, forcing it to speed away ever more quickly.
Astronomers came to the same conclusion about the universe. That some kind of energy in space must be pushing all the galaxies apart, causing the expansion to speed up. Because we don't see this energy, the astronomers called it dark energy.
It's among the most important experimental discoveries ever in the history of science.
It took most of us completely by surprise.
And so we're still trying to come to grips with that.
Discovering that dark energy is pushing every galaxy in our universe away from every other at an accelerating rate was shocking enough. But even more surprising was the strength of that dark energy. For over a decade, scientists have been unable to explain why such a peculiar amount of it exists in empty space. But that mystery seems easier to resolve if we're part of a much larger multiverse.
Now, the idea that space contains any energy at all sounds strange. But our theory of small things like molecules and atoms, the theory called quantum mechanics, tells us that there's a lot of activity in the microscopic realm, activity that can contribute in energy to space.
And according to the math, the amount of energy generated by that microscopic activity is enormous.
The problem is, when astronomers measure the amount of energy that's actually out there, the amount of energy required to force the galaxies apart at the accelerating rate that's observed, they get a number like this. A decimal point followed by 122 zeros and then a 1. An incredibly tiny amount, very close to 0, and nothing at all like what the theory predicted. In fact, it's trillions and trillions and trillions and trillions of times smaller. Colossal mismatch.
We have tried everything to explain why the dark energy is as small as it is. We have tried everything and everything fails.
Hopeless. I once called this the worst failure of an order of magnitude estimate in the history of science.
Does it bother us? Absolutely.
Finding that the amount of energy in space is so much less than our theory predicts is not just an academic problem. The precise strength of that repulsive gravity, well, that has profound implications for all of us. For example, if I were to increase the strength of the dark energy just a little bit, by erasing 4 or 5 of these zeros, I still have a tiny number, but the universe would be radically different.
That's because a slightly stronger dark energy would push everything apart so fast that stars, planets, and galaxies would never have formed. And that means we simply would not exist. And yet, here we are.
So, why is the amount of dark energy so much less than our theory predicts, and also just right to allow the formation of galaxies, stars, planets, and life? We just don't know. The mismatch between the theoretical predictions of dark energy and what astronomers have observed is one of the great mysteries that science faces today.
But consider this. If we do live in a multiverse, then the mystery of dark energy might not be so mysterious after all. In fact, if we're part of a multiverse, the value of dark energy we've measured might actually make total sense.
Hi, reservation for green. To see how the multiverse might solve the dark energy puzzle, imagine you're checking into a hotel and you get a room number like this. 10,000,001. Thanks.
Enjoy your stay.
10,000,001 would seem like a pretty strange room number, and getting a room number like this would be surprising, much as the value of dark energy in our universe is a number that scientists have found surprising. But here's the thing. If this hotel had a huge number of rooms, say billions and billions, then getting room number 10,000,001 wouldn't be so surprising.
In a hotel this big, you expect to find a room with that number. Similarly, if we're part of a multiverse with a huge number of universes, each with a different value of the dark energy, then you'd expect to find one with the value as small as what we've measured.
If you think of each of these rooms as a universe,
and each universe has a different value for the dark energy, then most of these universes won't be hospitable to life as we know it. The reason is that the value of the dark energy wouldn't allow the formation of galaxies, stars, and planets. Universes with much less dark energy than ours would collapse in on themselves. And universes with much more dark energy than ours would expand so fast that matter would never have the chance to coalesce into clumps and form stars and planets.
So, of course we find ourselves in a universe where the value of the dark energy is hospitable to life. Otherwise, we wouldn't be here to talk about it.
So, if we're part of a multiverse, the mystery of dark energy becomes not so mysterious. But there's a piece of the puzzle missing. How do we know if there's enough diversity within the multiverse to include every value for dark energy, even the strange value we observe in our universe? The answer would emerge from an entirely different area of physics. I'm talking about a groundbreaking theory that comes from investigating the universe on the tiniest scale. We know that inside atoms are even tinier bits of matter, protons and neutrons, which are made of still smaller particles called quarks. But physicists realize that this might not be the end of the line. These subatomic bits might actually be made of something even smaller. Tiny vibrating strands or loops of energy called strings. This set of ideas, called string theory, says everything that exists is made of this one kind of ingredient. And just as a single string on a cello can produce many different notes depending on how it vibrates, strings can take on different properties depending on how they vibrate, creating many kinds of particles. From this theory came the promise of elegant simplicity, a single master equation that would explain what we see in the world around us.
String theory would be beautiful, it would be elegant, and calculation from that very simple theory would produce the world as we know it.
But for this beautiful theory to work, there was a catch. The math of string theory required something that defies common sense. A feature that would open another door to the multiverse. Extra dimensions of space. We're all familiar with 3 dimensions of space: height, width, and depth. But the math of string theory says these aren't the only dimensions.
The mathematics works only if the strings move and vibrate, not just in the 3 directions that we see, but in those and, say, 6 more, 9 space dimensions in all.
So if string theory is right, where are these extra dimensions? And why can't we see them? Think about the cable supporting a traffic light. From a distance, it looks like a line, one-dimensional. But if you could shrink down to, say, the size of an ant, you'd find another dimension, a circular dimension that curls around the cable. And string theory says that if we could shrink down billions of times smaller than that ant, we'd find tiny extra dimensions like this are curled up everywhere in space.
At every point of space, there's extra dimensions of space that are curled up into little tiny knots that you can't see because they're too small.
And the shape of those extra dimensions determines the fundamental features of our universe.
Just the way the air streams that are going through an instrument like a French horn have vibrational patterns that are determined by the shape of the instrument, the shape of the extra dimensions determines how the little strings vibrate. Those vibrational patterns determine particle properties. So all of the fundamental features of our universe may be determined by the shape of the extra dimensions.
The way those extra dimensions of space are put together is in many respects like the DNA of the universe. They determine the way the universe is going to behave, just exactly the same way as DNA determines the way an animal is going to look.
The problem was, the more string theorists looked, the more ways they found that extra dimensions could be curled up. And the math provided no clues as to which shape was the right one corresponding to our universe.
I think the consensus right now is that that number seems to be astronomical. There are published papers suggesting upwards of 10 to the 500. That's 10 followed by 500 zeros, different possible shapes.
10 to the 500 different possible shapes for the extra dimensions, each appearing equally valid. It seemed preposterous, especially for a theory that was looking for one single master equation to describe our universe. But then it occurred to some string theorists that perhaps there was a different way to look at the problem. And this different perspective would breathe new life into the idea of a multiverse.
10 to the 500 different string theories. This sounded like a complete disaster. What good is it to have a theory that has 10 to the 500 solutions? You can't find anything in there. Well, that left string theorists somewhat unhappy, somewhat depressed. My own reaction to it at the time is, this is great, this is fantastic, this is exactly what the cosmologists are looking for. Enormous diversity of possibilities. Don't be unhappy about this. This says that string theory fits extremely well with cosmology and with all the interesting ideas about multiverses.
Turning what seemed like a vice into a virtue, some string theorists became convinced that the multiple solutions of string theory might each represent a real and very different universe. In other words, string theory was describing a multiverse, and an extremely diverse one at that.
To everyone's surprise, string theory was actually quite readily describing huge numbers of different kinds of solutions, each of which corresponds to a possible universe.
So we just got this multiverse for free.
Both from string theory and from inflation, you have these universes that are produced. These different universes would all naturally have different amounts of dark energy.
In fact, according to the math, the amount of dark energy would span such a wide range of values from universe to universe that the strange amount we've measured in our universe would surely be among them.
String theory, without even trying, solved that problem.
So, over a decade after Linde and Vilenkin had come up with their ideas about eternal inflation, the multiverse was revived. 3 lines of reasoning were now all pointing to the same conclusion. Eternal inflation, dark energy, and string theory. Just the way it takes 3 legs to support a stool, these 3 ideas, taken together, support the argument that we may live in a multiverse.
When different lines of research all converge on one idea, that doesn't mean it's right, but when all the spokes of the wheel are pointing at one idea, that idea becomes pretty convincing.
Today, the multiverse is hotly debated.
In the universe,
Many critics remain.
David Gross is going to tell us no, no, no.
But multiverse advocates like Alex Vilenkin, Alan Guth, and Andre Linde are no longer alone.
The tide appears to be turning, and now these ideas are accepted to a much larger degree.
Genie is out of the bottle. You cannot put it back.
So, what would it be like if we could travel to some of these other universes? What would we see? Some might be vastly different from our own, with properties unlike anything we've ever seen. In fact, some universes in the multiverse might not have ordinary matter or anything recognizable at all. And there might be other universes with features not unlike the familiar ones we know, but where life takes a completely different form, perhaps communicating in ways we'd find utterly bizarre. And the math shows that if we were able to visit enough of these universes, we might eventually find ones like ours, with a Milky Way galaxy, a solar system, and an Earth. Except with some slight differences. In one, maybe the asteroid that killed off the dinosaurs 65 million years ago missed. And evolution charted a new course. In another, there might be an Earth with people similar to us, but better at multitasking. But there's something even stranger. Somewhere out there, we should find exact copies of our universe with duplicates of everything and everyone. But how could this be? How could there be exact duplicates of ourselves out there in the multiverse?
To see how, take this deck of cards.
It's made up of 52 different cards, and if I deal them, everyone will get a different hand. But over the course of many, many rounds, eventually, some of the combinations will start to repeat.
That's because with 52 cards, there's a limited number of different hands you can deal. So if you deal the cards an infinite number of times, then repeating hands are inevitable. And in the multiverse, a similar principle applies.
That's because, according to the laws of nature, the fundamental ingredients of matter, or particles, are kind of like a deck of cards. In any region of space, they can only be arranged in a finite number of different ways. So, if space is infinite, if there are an infinite number of universes, then those arrangements are bound to repeat. And since each one of us is just a particular arrangement of particles, somewhere there's a duplicate of you and me and everyone else.
This can be shocking.
It could be that in another universe I was a rock star and my life is much better, or much worse, depending on your opinion of rock stars.
That means all those things that I've never found time to do are maybe being done by some copy of me somewhere else.
I was rather depressed, actually. This picture robs us of our uniqueness.
It is a consequence of the ideas, and the ideas seem very well motivated.
Yet, critics argue the multiverse is just too convenient an explanation for things we don't understand, like the tiny value of dark energy in our universe and the huge number of possible shapes for the extra dimensions in string theory.
The problem with that kind of reasoning is that it doesn't explain why dark energy is the way it is. It just says it's random chance.
I don't find that satisfactory. You can apply this kind of reasoning anytime you don't have a better explanation.
On the other hand, supporters of the multiverse point out that sometimes a better or deeper explanation for the way things are simply does not exist. Take, for example, the Earth's orbit around the Sun. We find ourselves at a distance of 93 million miles. Perfect for life. If we were much closer to the Sun, our planet would be too hot for life as we know it to exist. And if we were much farther from the Sun, it would be too cold for life. So why are we in this sweet spot? Well, starting in the late 1500s, the famous astronomer Johannes Kepler asked that very question. And he spent years trying to find a physical reason, some law of nature that requires the Earth to be 93 million miles from the Sun. But Kepler never found it, because it doesn't exist. There isn't any physical law requiring the Earth to be 93 million miles from the Sun. It's simply one possibility of the many you'd expect to find in a universe we know is full of solar systems.
You might think it was an extraordinary accident. It's not. It's just that there are a lot of planets out there.
Similarly, some suggest that the true explanation for some of the fundamental features of our universe will elude us if we don't consider the possibility that we live in a multiverse.
Clearly, if we had a good physical reason, that would be great, and we would understand it. We'd be much happier.
We may have to live with that. There's no principle built into the laws of nature that say that theoretical physicists have to be happy.
It's a hypothesis. It's the leading hypothesis because nobody has another hypothesis which makes as much sense.
The multiverse, a tantalizing possibility. But with no experimental evidence, should you believe it?
We can't believe in anything until there's observational or experimental support. But what we have found over the last few centuries is that mathematics provides a sure-footed guide to the nature of things that we haven't yet been able to see, observe, or experiment with.
Math predicted things like black holes and certain subatomic particles long before we ever observed them. And math is suggesting that there may be these other universes. That doesn't mean it's right, but often it's leading you to a deeper understanding of reality.
If you choose not to believe it, that's perfectly fine, because we have not given you any evidence yet. And One of the wonderful things about science is it's about evidence. It's not about belief.
And some scientists now think we might just be able to find that evidence. They propose that if our universe and another were born close together, the two might have collided. That collision could have left its own fingerprints, ripples in the cosmic background radiation that we might one day be able to detect.
My guess is, yes, that in 100 years we will know one way or another whether these ideas are right.
100 years from now, it may be an amusing historical episode. We don't know. But if you only work on the things that are already well established, you're not going to be part of the next big excitement.
If we do verify the multiverse, it would change our perspective much as Copernicus did 500 years ago when he showed that the Earth is not the center of the cosmos. And some might say that if our universe is just one of many, our descent from the center would be complete.
Regardless, I think it's more important just that we're so lucky that we can understand the universe.
I think it's a great ride, and I think it's really good for physics that we have this tension. I don't know where I'm going to end up.
So, what does this all mean? Are there infinite duplicates of you and me and everything existing right now in an infinite number of other universes? Is the multiverse the next Copernican revolution? We don't know, at least not yet. But if the idea that we live in a multiverse proves true, we'd be witnessing one of the most exciting and dramatic upheavals to our understanding of the fabric of the cosmos.
To order The Fabric of the Cosmos on DVD or Blu-ray, or to purchase the companion book, visit shoppbs.org or call 1-800-PLAY-PBS. The series is also available for download on iTunes.